Hi everyone and welcome to the channel. Today we are going to explore radar vegetation index monitoring using Sentinel-1 SAR imagery in Google Earth Engine. In this video we'll use a simple example just to demonstrate how RVI can be calculated using Sentinel-1 SAR data in Google Earth Engine. It is to know that this kind of SAR-based vegetation monitoring is especially powerful in regions where optical imagery is frequently obscured by clouds or haze. Here, by tracking the evolution of RVI across multiple polygons, we can gain valuable insights into, for example, vegetation health, water stress under drought conditions, and spatial patterns of impact after severe meteorological events. It's important to understand that this approach can be scaled up significantly. We will see this at the end of the tutorial. So let's get started. So first thing to do is to go to Earth Engine platform and to connect you to the code editor. If you have a GCP, a Google Cloud Platform organization or project linked to a code editor, a Google Earth code editor, you can of course connect you with the code editor inside your GCP. But I will show you how to do this with a simple Google account. So you click on the code editor. Here you have a new window. Maybe you will have to connect you with your Google account, of course. And you see this new window. At the top left you see the scripts. Here you have all of the Earth Engine documentations. And here you have your assets that are linked to your project. In the middle you will find the code editor where you will write your geospatial code. At the top right you will see the console. Basically it's here where you could print your insights or maybe your chart, or here that you will see all of the error handling or so, and you will have here all of the tasks just ingest within your project. Of course, last thing here is to see that you have a geospatial visualization. So here the first thing of ours today will be to import a shapefile here that will represent our area of interest, and before that we will see very quickly how to do this in QGIS. So maybe you will have to merge all of the agricultural crops. So here you will have to open the processing toolbox here and to write merge. Here you will see this algorithm that I have recently used, for example, but basically you will find it in Vector Générale. So you open it, here you have the 3 points, you select all of the layers, you make OK, you choose the right CRS for your project, and you can save the new layer in your desktop. Good. So here you see that all of the layers just have been merged. You can remove all of the previous layer, and here that's the layer we want to import into Google Earth Engine. And here in the menu assets you will click on the new and you will import a new shapefile. You will have to select a sources file. So for example I choose this one. You select all of the files and you can rename your file here. We'll call it like that, parcels, and be sure that it's on the right assets. You can upload this new vector file in your assets. You see that a new window just appeared in tasks. You see that Google is trying to ingest your new table. You see that the tasks have been submitted to the server. So after a while, yes, you see that the table have been well imported. So here you can refresh the window and you see parcels here. If you click on it, you will see the asset details. You will see an overview of your table. You will see all of the features and the properties. Here there is no one. You can delete this table, you can share it or import it into your code editor. You see that it's a new variable, so here you can rename it. I will rename it parcels. So basically I will just show you. So here you have to write this code and if you want to display it, you will have to click on the Run button. You see that some polygons just appeared here, so basically you can center here and apply a zoom. So I think it would be okay. Great. Here you have some drawing tools, but we won't use it for today. Here you have the satellite view, and here you can see the layer that you have inputted. So here it's a very simple polygon. Here, if you just want to have the perimeter of all of the parcels, you will have to dissolve all of those polygons. And if I run it, I will apply a buffer to, I think, of 40, I don't know. And this, I will merge this. This, I will dissolve this. Dissolve this pattern. Yes, so I have my area of interest, so I can export this. So I upload this new layer. I call it AOI and I upload it. After that, you can go in my Earth Engine repo and you can copy and paste the script I linked in the descriptions that you can find on my YouTube description or in my GitHub too. And here, basically, if I run this process, you will see that a rectangular area of interest just appeared. And of course the RVI is calculated, but for this tutorial I will replace it with my AOI here that I will call study area. So I will have my variable here, and I think it will works too. So let's see together how it works. So this first step centers the map view on the predefined studio areas. After that, we load Sentinel-1 SAR image collection. So this is a really important step because we can upload the Sentinel-1 GRD collection. This is a ground range detected. This dataset contains pre-processed SAR images, so the GRD products are projected to ground range and are radiometrically calibrated. So we see all the bands that are available here. You have the image property and of course the term of use. So we apply a date filter here with focus on a 5-year period to observe medium-term vegetation dynamics. After that, we apply a spatial filter with the study area. After that, we select the VV polarization. So this is a vertical transmit, vertical receive. This is useful for detecting surface roughness and soil moisture. We also select the VH polarization, so the vertical transmit, horizontal receive. So it's more sensitive to volume scattering from the vegetations, for example, branches, leaves, and so on. So by selecting both VV and VH, we enable vegetation index calculation based on dual polarization. Here we filter the IY interferometric wide swath mode. This is the standard acquisition mode over land that balances high spatial resolution, about 10 meters, and wide swath around 250 kilometers. So it is ideal for time series and changes detections. And finally, we select the ascending orbit. So the satellite moves from south to north, usually capturing scenes in local nighttime or early morning. So this provides consistent lighting conditions and reduces thermal influence compared to the descending orbit. So finally, we only retrain the VV and VH bands for vegetation analysis. In the step 5, Here we compute the radar vegetation index, the RVI. So it is to know that the SAR backscatter is originally in decibel dB units. So we have to convert it into linear scale to correctly apply the RVI formula. So in the first sub-step here, we compute the RVI index. The higher RVI values means more volume scattering, so it means that it's denser or more complex vegetation, and the lower values means that it's sparse or no vegetation area. In the second sub-step, we apply a new filter. It is to know that SAR data is noisy due to speckle, so we need to apply a 30-meter median filter that will help us reduce this noise while preserving the vegetation structure. And with this third step, we preserve temporal info. We retrain metadata such as system time start, so we can use it in time series. So in the step 6, we compute the average RVI for all images in the collection and visualize it over the study area with a color palette. So basically we will have the blue, so this will be the low vegetation cover, and the green to yellow will means that it's a moderate to dense vegetation. So in the step 7 and 8, we define a subregion for a time series. We define a smaller region within the study area to analyze vegetation changes over time in more detail. In the step 9, we print a RVI time series chart that will be displayed in the console. Here you can see that the scripts have generated a radar vegetation index time series in a chart with all the values that have been computed. So I will run it again, and here you see the time series of RVI values. So you can of course display it with this tool and download the CSV or the SVG or even the image here. So you can close this window. If you need more details or if you have some issues, don't hesitate to comment this video. We can generate Sentinel-1 backscatter time series 2. So it's here. It's another chart that shows how the raw backscatter in decibel for VV and VH polarizations changes over time. So you see that the VV tends to show the surface properties, for example, soil moisture, roughness, and the VH is more responsive to vegetation structure. So it can help interpret the RVI behavior in context. So you can download the CSV with all the values and download the image. Finally, you can display the RVI for this year. So if we zoom a little bit, we will see the agricultural crops that have been computed with the RVI. If we zoom a little bit, you will see the displayed images over the agricultural crops. Of course, we can export the images, so if you click here, you can run it, and of course you can export it into your cloud storage in the GCP, the Google Cloud Platform, or you can export it in your drive or add it to your assets, of course. Finally, you can export it. Yes, this is this step that allows us to export our images. So with this simple script, we exported a single RVI image and chart over agricultural crops, but it's important to know that this process can be fully automated using cloud infrastructure. We can monitor agricultural land, forest, or any land surface. This allows us to gain valuable insight to optimize, for example, water usage, respond to drought conditions, and identify the most impacted zones within each parcel, for example, and monitor land vegetation. So good luck with your GIS project. Don't hesitate to subscribe to the channel and write a comment if you need more specific tutorials.